Right now, as you watch this video, something extraordinary is happening in our cosmic neighborhood. A visitor from beyond our solar system, a wanderer that has traveled for potentially millions of years through the vast darkness between stars, is passing through our celestial backyard. And this isn't just any interstellar traveler. This object, known as Comet 3I Atlas, has done something that shocked astronomers worldwide. Something that even the famous Oumuamua, our first confirmed interstellar visitor, never accomplished. What you're about to discover will change how you think about our place in this universe and the hidden highways connecting distant stellar systems. If you are curious about that cosmic mystery, make sure to subscribe to the channel and give a thumbs up. I am just starting, and your support means a lot to me. Now let me take you back to October 2017. That's when astronomers detected something that made the scientific community erupt with excitement. An object, later named Oumuamua, a Hawaiian word meaning scout or first messenger from afar, was spotted racing through our solar system on a trajectory that made no sense. It wasn't orbiting our sun in a nice, predictable ellipse like asteroids and comets we'd studied for centuries. Instead, it was following a hyperbolic path, meaning it came from somewhere else, swung past our sun, and was heading back out into the cosmic void. Oumuamua became an instant celebrity in the astronomy world. Here was physical proof that objects travel between star systems, that our solar system isn't some isolated island in space, but rather a port of call on interstellar trade routes that have existed for billions of years. Scientists scrambled to point every available telescope at this mysterious visitor, desperate to learn everything they could before it vanished forever into the darkness. But Oumuamua was frustratingly shy about revealing its secrets. By the time astronomers realized what they were looking at, the object was already speeding away from us. It appeared as nothing more than a tiny point of light, even in our most powerful telescopes. Was it a comet? An asteroid? Something else entirely? The debates raged and continue to this day. Some measurements suggested it was tumbling through space like a cosmic football. Others proposed it might be oddly elongated, perhaps 10 times longer than it was wide. A few bold scientists even speculated, controversially, that it might be artificial, though mainstream astronomy firmly rejected this idea. The mystery deepened when researchers noticed Oumuamua was accelerating slightly as it moved away from the sun, faster than gravity alone could explain. Comets do this all the time when ice on their surface vaporizes, creating jets of gas that act like tiny rocket engines. But Oumuamua showed no signs of such outgassing, no visible tail or coma, the fuzzy cloud of gas and dust that typically surrounds active comets. It was an enigma wrapped in a puzzle, and it left us with far more questions than answers. Then, in August 2019, amateur astronomer Borisov discovered our second confirmed interstellar visitor using a telescope he'd built himself. This object, designated 2I Borisov, behaved much more like astronomers expected an interstellar comet to behave. It had a visible coma, a tail, and showed all the classic signs of a comet actively releasing gas and dust as the sun's warmth reached its icy surface. Scientists were thrilled. Finally, an interstellar visitor that played by the rules, that matched their predictions and models. 2I Borisov gave astronomers a chance to redeem themselves after the Oumuamua surprise. This time they were ready. Telescopes around the world and in space coordinated an unprecedented observing campaign. The Hubble Space Telescope captured stunning images, showing the comet's tail streaming behind it like cosmic hair caught in a solar wind. Spectroscopic analysis revealed its chemical composition, showing it contained water, carbon monoxide, and other compounds familiar from comets born in our own solar system. The observations of 2I Borisov taught us something profound. Comets from other star systems aren't necessarily exotic or alien in composition. The chemistry that created our solar system's comets apparently works the same way in other stellar nurseries scattered throughout the galaxy. We're all made from the same cosmic recipe, just cooked in different kitchens spread across the Milky Way. For several years after 2I Borisov's departure, astronomers waited eagerly for the next interstellar visitor. They improved their detection systems, developed better protocols for rapid response, and debated what surprises the next cosmic wanderer might bring. Would it be another well-behaved comet like Borisov? Or would it be strange and puzzling like Oumuamua? Then came July 1st, 2025. The Atlas Survey Telescope in Rio Hurtado, Chile, part of a network designed to detect asteroids that might pose a threat to Earth, spotted something unusual. The Asteroid Terrestrial Impact Last Alert System, ATLAS for short, is humanity's early warning system, constantly scanning the skies for potentially dangerous space rocks. But on this particular night, ATLAS found something far more intriguing than a local asteroid. The object's motion across the sky immediately caught the attention of astronomers at the Minor Planet Center, the organization responsible for cataloging small bodies in our solar system. When they calculated its orbit, they realized something extraordinary. This wasn't another asteroid or comet from our solar system's distant reaches. The mathematics were unmistakable. This object was following a hyperbolic trajectory, just like Oumuamua and Borisov before it. We had our third confirmed interstellar visitor. The discovery set off a flurry of activity in the astronomical community. Researchers immediately began searching through archived telescope data, looking for earlier observations of the object that might have been overlooked. Their detective work paid off. The Zwicky Transient Facility at Palomar Observatory in California had captured images of the comet dating back to June 14, 2025. 3 different ATLAS telescopes around the world had also recorded it passing through their fields of view. Suddenly, astronomers had nearly 3 weeks of observations to work with instead of just a few days. This extended observational timeline proved crucial. With nearly 3 weeks of data, astronomers could calculate 3I Atlas's orbit with remarkable precision. They could trace its path backward through time, following its journey through our solar system in reverse. And when they did, the results were absolutely clear. This comet didn't originate from the Oort cloud, that vast sphere of icy bodies surrounding our solar system at enormous distances. It didn't come from the Kuiper belt beyond Neptune, where Pluto and countless other frozen worlds orbit. 3I Atlas came from somewhere far beyond our sun's gravitational influence, from the space between stars. The name itself tells the story of this discovery. The 3 indicates this is the third confirmed interstellar object we've detected. The I stands for interstellar, a designation that sets it apart from the countless asteroids and comets native to our solar system. And Atlas credits the survey system that first reported it to the scientific community. It's a simple naming convention, but it represents something profound. We're now living in an era where visitors from other star systems are becoming a regular part of our astronomical experience. But here's where things get truly fascinating, where 3I Atlas begins to separate itself from its interstellar predecessors. When the Hubble Space Telescope turned its gaze toward this cosmic wanderer on July 21, 2025, it captured something spectacular. The images revealed a teardrop-shaped cocoon of dust streaming away from the comet's nucleus, a glowing shroud of material being blown backward by the solar wind and radiation pressure from our sun. Now you might be thinking, didn't Borisov also show a coma and tail? Yes, absolutely. But here's the crucial difference, the thing that makes 3I Atlas special. The sheer number of observations we're gathering, the coordination between different telescopes and spacecraft, and the duration of our observing campaign are unprecedented. We're not just glimpsing this interstellar visitor as it races past. We're studying it in detail over many months, watching how it changes and evolves as it approaches the sun. The Hubble observations revealed something else intriguing. Because the telescope was tracking 3I Atlas as it moved against the background stars, those distant suns appear as streaks in the images rather than points. It's like photographing a moving car from another moving car. The background blurs while your subject stays sharp. This technique allows Hubble to gather detailed information about the comet itself, while the stellar backdrop becomes a streaked curtain of light. Astronomers analyzing Hubble's data as of August 20, 2025, have been working to determine the size of 3I Atlas's nucleus, the solid, icy core at the heart of all that dust and gas. Their calculations indicate the nucleus could be as large as 3.5 miles, or 5.6 kilometers, in diameter. But there's uncertainty here, as there always is when studying objects hundreds of millions of miles away. The nucleus might be considerably smaller, perhaps only 1,444 feet, or 440 meters across. Why such a large range in the size estimate? It comes down to the challenges of observing a small, dark object surrounded by a bright cloud of dust and gas, all of it incredibly distant from Earth. When Hubble captured those July images, 3I Atlas was 277 million miles away. That's almost 3 times the distance between Earth and the Sun. Imagine trying to measure the size of a snowball in Los Angeles while standing in New York, and that snowball is surrounded by fog. That's essentially what astronomers are attempting. But unlike Oumuamua, which disappeared before we could gather comprehensive data, 3I Atlas is sticking around for an extended performance. The comet will remain visible to ground-based telescopes through September 2025, giving astronomers months to study it in detail. Then, as it swings around the Sun and passes too close for safe observation, the Sun's glare would overwhelm any telescope trying to observe it. There will be a brief intermission. By early December 2025, 3I Atlas will reappear on the far side of the Sun, like an actor returning for a curtain call. This will allow for renewed observations as the comet begins its journey back out into interstellar space. The entire observing campaign will span many months, providing an unprecedented opportunity to watch an interstellar visitor throughout much of its passage through our solar system. The comet's closest approach to the Sun will occur around October 30th, 2025, when it reaches a distance of about 1.4 astronomical units. That's roughly 130 million miles, or 210 million kilometers, just inside the orbit of Mars. For perspective, Earth orbits at 1 astronomical unit from the Sun, so 3I Atlas will venture slightly closer to our star than our own planet does. Some of you might be wondering, should we be worried? Is this interstellar visitor a threat to Earth? The answer is an emphatic no. 3I Atlas poses absolutely no danger to our planet. Its closest approach to Earth will occur at a comfortable distance of about 1.8 astronomical units, roughly 170 million miles, or 270 million kilometers. That's farther away than the Sun is from us. We're perfectly safe, free to observe and study this cosmic traveler without any concern. Now let's talk about what makes 3I Atlas's discovery and ongoing observation campaign truly revolutionary. When Oumuamua blazed through our solar system in 2017, it caught us completely by surprise. By the time astronomers realized what they were seeing, the object was already on its way out. We managed to gather some observations, but they were rushed, limited, and left us with more questions than answers. It was like meeting someone fascinating at a party, having a brief conversation, and then watching them leave forever before you could ask all the questions burning in your mind. With 2I Borisov in 2019, we did better. We had more warning, better coordination, and managed to conduct a respectable observing campaign. But even that effort pales in comparison to what's happening with 3I Atlas. This time, the astronomical community is pulling out all the stops. NASA alone is marshaling an armada of spacecraft and telescopes to study this visitor, a fleet that reads like a who's who of space exploration. Speaking of rare cosmic objects, if you think interstellar comets are extraordinary, wait until you see what I cover in my video called The Rarest Objects in the Universe. We're talking about objects so scarce that 3I Atlas might seem common by comparison. If you are interested, the link is in the description and pinned on the comments. The Hubble Space Telescope, humanity's most famous orbital observatory, continues capturing detailed images as 3I Atlas moves through our neighborhood. The James Webb Space Telescope, the most powerful space telescope ever built, is training its infrared eyes on the comet, potentially revealing details about its composition and temperature that no other instrument can detect. Webb's ability to see infrared light means it can peer through dust clouds that would blind optical telescopes, possibly revealing the comet's nucleus more clearly than ever before. But the observation campaign extends far beyond just these two famous telescopes. The Transiting Exoplanet Survey Satellite, known as TESS, which normally searches for planets around distant stars, is also turning its attention to 3I Atlas. The Swift spacecraft, designed to detect gamma-ray bursts from the far reaches of the universe, will contribute its unique perspective. Even SphereX, a mission designed to map the entire sky in infrared light, will gather data on this interstellar wanderer. Here's where things get even more exciting. We're not just observing 3I Atlas from Earth's vicinity. NASA's fleet of Mars spacecraft will have a unique vantage point as the comet makes its closest approach to the Sun. The Perseverance rover, currently exploring Jezero crater on the Martian surface, might capture images of the comet from the red planet's perspective. The Mars Reconnaissance Orbiter, circling Mars from above, will add its observations to the growing dataset. Even the Curiosity rover, Perseverance's older cousin exploring Gale crater, might get in on the action. Think about what this means for a moment. We're coordinating observations of an interstellar visitor from multiple planets. Humans on Earth and our robotic explorers on Mars will be studying the same cosmic object simultaneously, gathering data from different angles and distances. This is the kind of multi-planetary science that would have seemed like pure fantasy just a generation ago. The observation campaign extends even further into the solar system. The Europa Clipper spacecraft, on its way to study Jupiter's icy moon Europa, will observe 3I Atlas during its journey. The Lucy mission, designed to explore asteroids that share Jupiter's orbit, will contribute observations. The Psyche spacecraft, headed toward a metal-rich asteroid between Mars and Jupiter, will also participate. Each of these missions will provide unique data points, helping astronomers build a comprehensive picture of our interstellar visitor. Even spacecraft near the Sun itself will join the effort. The Parker Solar Probe, which dives closer to our star than any human-made object in history, will observe 3I Atlas from its unique perspective deep within the Sun's corona. Punch, a mission studying how the Sun's corona flows out into space as the solar wind, will track the comet as it passes through different regions of solar influence. The joint ESA and NASA Solar and Heliospheric Observatory, known as SOHO, which has discovered thousands of comets passing near the Sun, will keep its instruments trained on 3I Atlas during its closest solar approach. And we can't forget about the European Space Agency's JUICE mission, currently on its way to explore Jupiter's icy moons. Even from its distant vantage point, JUICE will contribute observations to this unprecedented campaign. It's a truly international multi-spacecraft effort that demonstrates how far our capability to explore and study the cosmos has advanced. But here's the question that's probably forming in your mind. What exactly are all these telescopes and spacecraft looking for? What can we learn from 3I Atlas that we couldn't learn from Oumuamua or 2I Borisov? The answer lies in the details, in the subtle differences and similarities that reveal the hidden nature of interstellar space and the planetary systems where these wanderers originated. First and foremost, astronomers want to understand the comet's composition. What is 3I Atlas made of? Is it primarily water ice, like many comets in our solar system? Does it contain frozen carbon dioxide, carbon monoxide, or more exotic ices? The James Webb Space Telescope's infrared spectrographs can detect the specific wavelengths of light absorbed and emitted by different molecules, creating a chemical fingerprint of the comet's material. This chemical analysis isn't just academic curiosity. The composition of 3I Atlas tells us about the stellar system where it formed, potentially billions of years ago. Different stars have different metallicities, different abundances of elements heavier than hydrogen and helium. The planets, asteroids, and comets that form around these stars inherit these chemical signatures. By analyzing 3I Atlas, we're essentially sampling material from another planetary system without having to travel light years to get there. Early spectroscopic observations are already revealing fascinating details. The dust streaming away from the comet's nucleus appears to contain silicate particles, compounds of silicon and oxygen similar to the minerals that make up much of Earth's crust. This suggests that wherever 3I Atlas formed, the basic chemistry wasn't dramatically different from our own solar system. Silicon, oxygen, carbon, and other elements combined in familiar ways, creating materials we would recognize. But there might be subtle differences, too. Perhaps the ratios of different isotopes, versions of the same element with different numbers of neutrons, will reveal something unique about the stellar nursery where 3I Atlas was born. Maybe the abundance of certain rare elements will point toward a star older or younger than our Sun, or one with a different mass and temperature. These are the kinds of details that transform an interesting discovery into a profound scientific revelation. Scientists also want to understand how 3I Atlas is changing as it approaches the Sun. Comets are dynamic objects, not static chunks of ice floating through space. As they get closer to the Sun, solar radiation warms their surfaces, causing ices to sublimate, to transition directly from solid to gas without becoming liquid first. This process creates the coma and tail that make comets so spectacular to observe. By watching 3I Atlas over many months, astronomers can track how its activity level changes with distance from the Sun. Does it follow the same patterns as comets native to our solar system? Or does it behave differently, perhaps because its composition is subtly exotic, or because it formed under different conditions than our local comets? Every measurement, every observation adds another piece to the puzzle. The rotation rate of the comet is another crucial piece of information. How fast is 3I Atlas spinning? Is it tumbling chaotically through space, or does it have a stable rotation axis like Earth? The rotation can tell us about the comet's history, whether it's been involved in collisions, how its mass is distributed, and how forces acting on it during its long journey have affected its motion. Here's where 3I Atlas has a massive advantage over Oumuamua. With that first interstellar visitor, we caught only a glimpse before it vanished. The rotation measurements were uncertain and controversial. Some analyses suggested a tumbling motion, others a more stable spin. We simply didn't have enough data to be certain. With 3I Atlas, we have months of observations from multiple instruments. The uncertainties will be much smaller, the conclusions much more robust. The nucleus size determination is another area where 3I Atlas represents a major step forward. As I mentioned earlier, current estimates place the nucleus diameter somewhere between 440 meters and 5.6 kilometers. That's a huge range, but it's already more precise than what we knew about Oumuamua for years after its discovery. As observations continue and astronomers develop more sophisticated analysis techniques, that range will narrow considerably. Understanding the size matters for several reasons. First, it tells us about the population of objects drifting through interstellar space. Are most of these wanderers relatively small, like asteroids? Or are there substantial numbers of larger bodies, kilometers across, traveling between the stars? Second, size helps us understand the object's thermal properties, how quickly it heats up in sunlight and cools down in shadow. This affects the outgassing patterns that create the coma and tail. The shape of 3I Atlas is also under investigation. Is it roughly spherical, like many comet nuclei? Or might it be elongated, possibly resembling the controversial shape proposed for Oumuamua? The Hubble images showing the teardrop-shaped dust coma don't necessarily reveal the nucleus shape directly, but as more observations accumulate, astronomers will be able to infer the nucleus geometry from how sunlight reflects off it and how the dust distribution evolves. One of the most exciting aspects of 3I Atlas's passage through our solar system is the opportunity to test our theories about how interstellar objects navigate through space. You see, as a comet approaches the Sun, it doesn't just feel the star's gravitational pull. The outgassing we mentioned, the sublimation of ices creating jets of gas, also produces a force like tiny rocket engines firing from the nucleus surface. This outgassing force is what caused so much controversy with Oumuamua. The object accelerated slightly faster than gravity alone could explain, but it didn't show visible signs of cometary activity. This led to all sorts of speculation, from exotic explanations involving hydrogen icebergs to more controversial suggestions about artificial origins. With 3I Atlas, we can observe both the acceleration and the visible activity causing it, allowing us to test and refine our models. The trajectory of 3I Atlas has been calculated with impressive precision thanks to all those observations dating back to mid-June. Astronomers have traced the comet's path backward through time, determining where it came from before entering our solar system. Unlike planets and asteroids bound to our sun, which follow elliptical orbits that bring them back again and again, 3I Atlas follows a hyperbolic trajectory. An open curve that enters our solar system, swings around the sun, and heads back out, never to return. When traced far enough backward, the trajectory points toward a specific region of the sky, giving us a general direction of origin. This doesn't tell us exactly which star system 3I Atlas came from. The journey likely took so long that the stars have moved significantly since the comet began its voyage, but it gives us clues about the galactic neighborhood where this wanderer started its journey. Some quick calculations reveal the remarkable nature of interstellar travel. Our galaxy, the Milky Way, rotates as a whole, carrying its stars along like horses on a cosmic carousel. But stars also have their own individual motions relative to this overall rotation. 3I Atlas has been traveling through space between stars, carried along by whatever velocity it had when it left its home system. The distances involved are almost incomprehensible. Even the nearest star to our Sun, Proxima Centauri, lies about 4.2 light-years away. That means light, traveling at 186,000 miles per second, takes 4.2 years to make the journey. 3I Atlas isn't moving anywhere near the speed of light. It's traveling at tens of kilometers per second, fast by human standards but glacially slow on interstellar scales. This means 3I Atlas has likely been wandering through the galaxy for millions of years, possibly tens or even hundreds of millions of years. Think about what that means. This comet might have been ejected from its home system back when dinosaurs ruled Earth, or perhaps even earlier, when life on our planet consisted entirely of single-celled organisms. It's been traveling through the cold darkness of interstellar space longer than some species have existed on Earth. During that immense journey, 3I Atlas experienced temperatures close to absolute zero, just a few degrees above the coldest possible temperature in the universe. Far from any star's warmth, the comet's surface would have been frozen solid, its ices locked in a deep cryogenic sleep. Cosmic rays, high-energy particles accelerating through space, would have bombarded its surface, gradually altering its chemistry and creating new compounds through radiation-induced reactions. Interstellar dust grains, tiny particles drifting through the space between stars, would have pelted the comet's surface like microscopic meteorites. Over millions of years, this slow sandblasting would have eroded the surface, possibly creating a layer of radiation-processed material different from the pristine ices beneath. Some scientists call this altered surface layer a radiation mantle, and it might affect how the comet behaves when the sun's warmth finally reaches it. Now, here's where we get to the heart of what makes 3I Atlas special compared to Oumuamua. With our first interstellar visitor, we detected the object after its closest approach to the sun. It was already heading back out into the cosmos, and we were essentially looking at the back of a departing guest. We missed the show, arriving at the party after the main event had concluded. With 2I Borisov, we did better. We caught it on the approach and watched it throughout its passage. But our observational capabilities in 2019, while impressive, weren't as comprehensive as what we can deploy today. We didn't have the James Webb Space Telescope yet. Many of the spacecraft now contributing observations weren't in position or hadn't launched yet. We did good science with 2I Borisov, but we were working with a smaller toolkit. 3I Atlas represents the full maturation of our interstellar object observation capabilities. We detected it early enough to prepare properly. We have more and better instruments available than ever before. And critically, we have the time, months of observable time, to conduct a systematic, comprehensive study. This isn't a rushed observation campaign done in panic as an unexpected visitor races past. This is deliberate, methodical science at its finest. The coordination required to pull off this observation campaign is itself impressive. Imagine trying to schedule observation time on a dozen different telescopes and spacecraft, each with its own mission priorities and constraints. Hubble might be in the middle of a long-term study of distant galaxies. Webb has a packed schedule of observations that scientists have been waiting years to conduct. The Mars orbiters have their own responsibilities monitoring the red planet's atmosphere and surface. Yet the astronomical community recognized the extraordinary opportunity presented by 3I Atlas and mobilized quickly. Special observation windows were carved out, schedules were adjusted, and competing priorities were balanced against the once-in-a-lifetime chance to study an interstellar visitor with unprecedented thoroughness. This kind of coordination showcases the collaborative spirit that drives modern astronomy. The data flowing in from all these instruments is being shared rapidly among researchers worldwide. Unlike the old days when astronomers might hoard their observations, modern practice increasingly favors open data sharing, especially for time-sensitive phenomena. Scientists in Japan, Europe, the United States, and elsewhere are all analyzing the same datasets, bringing different expertise and perspectives to the interpretation. This collaborative approach accelerates discovery. Maybe a researcher in Germany notices something subtle in the spectroscopic data that a colleague in Australia can correlate with structural features seen in high-resolution images. Perhaps a team in Chile develops a new analysis technique that helps scientists in California better understand the comet's rotation. Science has always been a collective endeavor, but modern communication technology and data sharing practices have taken collaboration to new heights. Now let's address something that might be on your mind. How rare are these interstellar visitors? Are we just lucky to have spotted 3 in the past 8 years? Or does this detection rate tell us something about how many of these objects are actually out there? The answer reveals something fascinating about our solar system's place in a much larger galactic ecosystem. Astronomers have run computer simulations trying to estimate how many interstellar objects pass through our solar system. The results suggest that at any given moment, there might be several interstellar visitors inside Neptune's orbit, roughly 30 astronomical units from the Sun. Most of these would be too small and faint to detect with current telescopes. We're seeing only the tip of an enormous iceberg. Some estimates suggest that in the entire volume of space from the Sun out to Neptune's orbit, there might be 10,000 interstellar objects larger than 100 meters across at any given time. Most are just passing through, invisible to our instruments because they're small, dark, and far away. Only occasionally does one pass close enough and become active enough for us to notice. This realization fundamentally changes how we think about our solar system. We tend to imagine it as a discrete entity, a family of planets and smaller bodies all bound to our Sun and separate from other stellar systems. But really, our solar system is more like a train station with a constant flow of travelers passing through. Most travelers are our local comets and asteroids making their regular rounds, but there's also a steady stream of interstellar wayfarers just passing through on journeys that span the galaxy. 3I Atlas is one of these travelers that happen to come close enough and brighten enough for us to notice. The comet's path will bring it to about 1.4 astronomical units from the Sun, well within the orbital distance of Mars. At this range, solar heating is strong enough to vaporize surface ices efficiently, creating the visible coma and tail that make comets spectacular and detectable. But here's something crucial to understand. 3I Atlas won't linger in our neighborhood. After swinging around the Sun in late October 2025, the comet will head back out toward the outer solar system, accelerating as the Sun's gravity flings it outward like a stone from a sling. By the time it crosses Neptune's orbit again, it will be moving fast enough to escape the Sun's gravitational grip entirely. Within a few years, 3I Atlas will be back in interstellar space, continuing a journey that began millions of years ago in some unknown stellar system. The warmth it felt during its brief passage through our solar system will fade to a memory, preserved only in its slightly altered surface. The comet will return to the frozen darkness between stars, its encounter with our Sun just one brief episode in an unimaginably long voyage. Unless, of course, it encounters another star system somewhere in the distant future. The galaxy is vast, but it's also crowded on cosmic scales. There are between 200 billion and 400 billion stars in the Milky Way. Over millions or billions of years, 3I Atlas will likely pass near other stellar systems, perhaps even entering some of them as it entered ours. Maybe someday, in a future so distant our sun will have evolved into a red giant, 3I Atlas will give alien astronomers around another star the same thrill of discovery that it's giving us now. This brings us to one of the most profound questions raised by interstellar visitors. What do they tell us about planetary system formation and evolution? You see, these wandering comets and asteroids weren't born in interstellar space. They formed in planetary systems, probably during the chaotic early phases when planets were still assembling from the disk of gas and dust surrounding a young star. During planetary formation, gravitational interactions between growing planets can be violent. Picture the early solar system, numerous planetary embryos of various sizes orbiting the young sun, occasionally colliding and merging, their gravitational fields perturbing smaller objects. Computer simulations of this process show that many objects get ejected entirely from the system, flung out into interstellar space by close encounters with massive planets. Jupiter, our solar system's giant, probably ejected countless comets and asteroids during its formation and early migration. Some of those objects are still wandering the galaxy today, perhaps occasionally passing through other stellar systems just as 3I Atlas is passing through ours. In a very real sense, we've exported samples of our solar system to the rest of the galaxy, while simultaneously receiving samples from other systems. This cosmic exchange program means that the study of interstellar visitors like 3I Atlas isn't just about those specific objects. It's about understanding planetary system formation as a universal process. Are the comets ejected from other systems chemically similar to ours, suggesting that planet formation works the same way everywhere? Or are there differences that hint at variations in how different types of stars form their planetary families? The early data from 3I Atlas suggests broad similarity to our local comets, at least in basic composition. The presence of water ice and silicate dust points to formation processes fundamentally similar to what happened in our solar system. But the detailed analysis is still ongoing. Perhaps spectroscopic studies will reveal subtle isotopic ratios that differ from solar system norms. Maybe the abundance of certain trace elements will tell a different story. Science often hides its most interesting secrets in the details. One aspect that makes 3I Atlas particularly valuable is the ability to observe it during both inbound and outbound legs of its solar passage. When a comet approaches the sun, it heats up gradually. Different ices vaporize at different temperatures. Water ice, for instance, doesn't become significantly active until a comet gets inside about 3 astronomical units from the sun. More volatile materials like carbon monoxide can start outgassing at much greater distances when the comet is still far out in the cold outer solar system. By observing 3I Atlas throughout its entire passage, astronomers can track which materials become active at which distances. This creates a kind of chemical inventory, revealing the composition in a way that wouldn't be possible with just a brief snapshot. It's like watching a layer cake slowly melt from the outside in. Each layer reveals itself in turn, telling you about the structure and composition of the whole. The outbound observations will be particularly interesting because they'll show how the comet's activity winds down as it retreats from the sun. Does the activity decrease symmetrically, mirroring the increase that occurred during approach? Or are there asymmetries that hint at permanent changes to the nucleus surface? Sometimes comets develop insulating layers of dust during their solar passage, and these layers can significantly affect how quickly the comet deactivates as it moves back into the outer solar system. This kind of detailed behavioral study simply wasn't possible with Oumuamua. That object was discovered after its closest solar approach, already heading outbound. We missed the entire inbound leg, the period of increasing activity as it approached the sun. We couldn't observe the full cycle of heating and cooling that reveals so much about a comet's nature. With 3I Atlas, we're capturing the complete performance, from opening act to final curtain. The involvement of Mars-based assets in observing 3I Atlas adds another exciting dimension. Imagine the Perseverance rover looking up at the Martian sky and capturing an image of this interstellar visitor. That photograph would represent something unprecedented, a picture of an object from another star system, taken from the surface of another planet by a robot we built and sent there. The science value goes beyond just the cool factor, though. Observations from Mars provide a different viewing angle than Earth-based observations. This parallax, the apparent shift in position when viewed from different locations, helps astronomers better constrain the comet's exact position and trajectory. It's similar to how your brain uses the slightly different views from your two eyes to judge distances and create depth perception. Additionally, the Martian atmosphere is much thinner than Earth's and has different optical properties. Observations from Mars might reveal features or behaviors that are difficult to detect through Earth's thick, turbulent atmosphere. And timing is particularly favorable. In late 2025, when 3I Atlas reaches its closest approach to the Sun, Mars will be reasonably well positioned to observe the comet, though the exact geometry depends on the orbital positions of both planets at that time. The Parker Solar Probe observations will be extraordinary for entirely different reasons. This spacecraft routinely dives to within a few million miles of the Sun's surface, closer than any human-made object has ever ventured. From this vantage point deep within the solar corona, Parker can observe 3I Atlas passing through different regions of the Sun's extended atmosphere and the solar wind flowing outward into space. These observations will reveal how the comet interacts with the solar wind, the constant stream of charged particles flowing out from the Sun. The solar wind can strip material from a comet's coma, creating spectacular ion tails that point directly away from the Sun regardless of the comet's direction of motion. Parker's instruments can measure the properties of the solar wind before and after it encounters the comet, showing how the interaction affects both objects. The SOHO spacecraft has a legendary track record of comet discoveries. Since its launch in 1995, SOHO has discovered over 4,000 comets, mostly small sun grazers that pass extremely close to our star. While 3I Atlas won't pass nearly as close to the Sun as these sun grazers, SOHO's instruments are perfectly suited to observe comets in the inner solar system, and it will add valuable data to the observation campaign. One of SOHO's specialties is observing the region immediately around the Sun using a coronagraph, an instrument that blocks the Sun's bright disk to reveal fainter structures nearby. During the period when 3I Atlas passes too close to the Sun for most telescopes to observe safely, SOHO might be able to maintain observations, helping to fill what would otherwise be a gap in our data coverage. All of these observations from various spacecraft and telescopes are being carefully coordinated and timed. You can't just point an instrument at 3I Atlas whenever you feel like it. Each observatory has limited resources, competing priorities, and specific constraints. Hubble, for instance, orbits Earth every 97 minutes, and it can only observe objects when they're not blocked by Earth, and when the telescope isn't pointing too close to the Sun. Webb faces different constraints. As an infrared telescope, it must be kept extremely cold to prevent its own heat from overwhelming the faint infrared signals it's trying to detect. This requires Webb to always keep its sunshield between itself and the Sun, limiting which parts of the sky it can observe at any given time. Scheduling Webb observations of 3I Atlas requires careful planning to ensure the comet is in an observable part of the sky when the telescope can point there. Ground-based observatories face their own challenges. Weather can interfere with observations, clouds hiding the sky at crucial moments. The comet is only visible during certain hours of the night, and it must be above the horizon and in a dark enough sky to observe clearly. Astronomers at different latitudes around the world have different visibility windows, which is why international collaboration is so valuable. When the comet sets below the horizon at one observatory, it's rising at another. Despite all these challenges, the observation campaign is proceeding remarkably well. Data is accumulating, analyses are being conducted, and our understanding of 3I Atlas grows deeper every day. Preliminary results are already being shared at scientific conferences and through rapid publication journals designed to disseminate time-sensitive discoveries quickly. One of the early surprises, though perhaps it shouldn't have been surprising, is just how much 3I Atlas resembles comets from our own solar system. This might sound disappointing, like we were hoping for something wildly exotic and alien. But actually, this similarity is profoundly important. It suggests that the chemistry of planet formation, the processes that create comets, works essentially the same way around other stars as it does around our sun. Think about what this means. The universe isn't just vast, it's also remarkably uniform in its basic chemistry and physics. The laws of nature that govern how atoms combine into molecules, how molecules freeze into ices, and how ices aggregate into comets appear to be universal. 3I Atlas formed in another stellar system, possibly around a star different from our sun, yet the comet is fundamentally similar to the icy bodies that formed here. This uniformity has profound implications for the search for life beyond Earth. If the chemistry of planetary system formation is universal, then the building blocks of life, water, organic compounds, and other essential materials should be common throughout the galaxy. Wherever planets form, they'll likely be supplied with the raw materials needed for life, at least life as we know it. Of course, having the raw materials doesn't guarantee that life will emerge. There are countless other factors involved, from the stability of a planet's orbit to the presence of a protective magnetic field, from the right amount of atmospheric pressure to the fortunate timing of cosmic events. But at least we can say with increasing confidence that the universe isn't starving for the chemical ingredients life requires. Those ingredients are everywhere, even arriving from interstellar space aboard wandering comets like 3I Atlas. Speaking of which, there's a fascinating hypothesis that some scientists have proposed. Could interstellar comets actually spread life between star systems? The idea, called panspermia, suggests that microorganisms might survive the extreme conditions of interstellar space by hiding deep within cometary ice. When such a comet enters a new stellar system and deposits material on planets, it might seed those worlds with life. Now, this idea faces significant challenges. The interstellar environment is harsh. Cosmic radiation would penetrate deep into a comet over millions of years, potentially destroying any biological material. The cold is absolute, the vacuum is perfect, and there's no energy source to sustain metabolism. Yet we've discovered that some Earth microorganisms can survive in surprisingly extreme conditions, entering dormant states where they're neither fully alive nor completely dead. Laboratory experiments have shown that certain bacteria can survive years of exposure to space-like conditions. Some organisms produce hardy spores that resist radiation, temperature extremes, and desiccation. Whether these survival mechanisms could protect life forms over the millions of years required for interstellar travel remains an open question. But the discovery that interstellar comets regularly pass through planetary systems at least makes the logistics of panspermia somewhat more plausible than they seemed before we knew these objects existed. 3I Atlas won't be carrying any samples back to Earth for laboratory analysis. It's passing through our solar system without stopping. But every photon of light it reflects or emits carries information. Spectroscopy, the analysis of light's wavelength distribution, can identify specific molecules based on their unique spectral fingerprints. This technique has revealed water vapor, carbon dioxide, and various organic compounds in the Comet of solar system comets. Scientists are applying the same methods to 3I Atlas, building a chemical profile of this interstellar wanderer. Early spectroscopic data, though still preliminary as of the latest reports, shows signatures consistent with water sublimation and silicate dust. This matches expectations based on 2I Borisov observations, but every additional data point strengthens our statistical confidence. Are we seeing exactly the same chemical ratios as in solar system comets, or are there subtle differences that would be scientifically significant? The dust composition is particularly interesting. Dust grains ejected from comets are tiny, typically measured in micrometers, smaller than the width of a human hair. Yet these grains carry important information. Their composition reflects the materials available in the protoplanetary disk where the comet formed. Their size distribution tells us about the comet's internal structure and the processes ejecting them into space. Light scattering by dust grains also reveals their properties. When sunlight hits a dust particle, the way that light scatters depends on the particle's size, shape, and composition. By carefully analyzing the brightness and polarization of light reflected from 3I Atlas's coma, scientists can infer the properties of the dust grains without ever collecting a physical sample. It's detective work at the highest level, extracting maximum information from minimal evidence. Another aspect being studied is the comet's activity pattern. Some comets show steady, predictable outgassing that smoothly increases as they approach the sun and decreases as they depart. Others are more erratic, experiencing sudden outbursts where activity spikes dramatically for reasons that aren't always clear. These outbursts might result from sudden exposure of fresh ice when surface dust layers collapse, or from the vaporization of particularly volatile ice pockets within the nucleus. Has 3I Atlas shown any signs of unusual activity? As of the latest observations, the comet appears to be behaving in a relatively standard fashion, with activity levels increasing steadily as it approaches the sun. But astronomers are watching carefully for any deviations from expected behavior. An unexpected outburst could reveal something unique about the comet's structure or composition. The teardrop shape of the dust coma seen in Hubble images is particularly telling. This shape results from the combined effects of several forces. Dust is ejected from the nucleus by escaping gas, blown back by radiation pressure from sunlight, and curved by the comet's orbital motion. The exact shape depends on the dust grain sizes, the gas production rate, and the comet's speed and direction. Computer models can simulate how different combinations of these factors would create different coma shapes. By comparing the actual observed shape with simulated shapes, astronomers can work backward to infer properties like the dust-to-gas ratio in the material being ejected. This ratio is important because it tells us about the comet's composition, specifically how much dust is mixed in with the ice. The fact that we're seeing a prominent dust coma also confirms that 3I Atlas is definitely a comet rather than an asteroid. Asteroids are rocky or metallic bodies that generally don't sublimate much material when warmed by the sun. Comets, by contrast, are rich in volatile ices that vaporize readily. The clear cometary activity of 3I Atlas places it firmly in the comet category, unlike Oumuamua, whose classification remained ambiguous. This unambiguous identification as a comet makes 3I Atlas easier to study and understand. We have a century of comet observations to draw upon, countless models of cometary behavior, and a solid theoretical framework for interpreting our observations. We're not starting from scratch trying to figure out what kind of object we're looking at, as was the case with Oumuamua. The trajectory calculations for 3I Atlas have reached impressive precision. Astronomers can now predict the comet's position months in advance with accuracy measured in arc-seconds, tiny fractions of a degree. This precision is essential for scheduling observations, particularly for spacecraft with limited fields of view or narrow communication windows. These calculations also allow scientists to trace the comet's path far into the future. Where will 3I Atlas be in 10 years? In 100 years? In 1,000? The mathematics can answer these questions, showing the comet's predicted position as it climbs back out of the sun's gravity well and returns to interstellar space. By the year 3000, 3I Atlas will be far beyond the orbits of even our most distant known planets, continuing its journey through the galaxy. And what about tracing the orbit backward? This is where things get speculative but fascinating. By running the orbital calculations in reverse, astronomers can determine the general direction from which 3I Atlas approached our solar system. The calculations show the comet coming from a specific region of the sky, a particular constellation as seen from Earth. However, determining the exact star system of origin is virtually impossible. Even if 3I Atlas has been traveling only a few million years, a short time on cosmic scales, the stars in our galactic neighborhood have all shifted positions significantly. The star nearest to 3I Atlas's origin point today probably wasn't there when the comet began its journey. It's like trying to identify which specific house a drifting leaf came from in a city where all the houses are constantly moving. Despite this limitation, There's something profound about knowing the general direction of 3I Atlas's origins. When you look up at that particular patch of sky, you're looking toward the region of our galaxy where this ancient traveler began its journey. Somewhere in that direction, though we can't pinpoint exactly where, there's a stellar system that ejected this comet millions of years ago. Perhaps planets orbit that distant sun. Perhaps those planets harbor life. Perhaps intelligent beings on one of those worlds once looked up at their night sky and wondered, just as we do, whether they're alone in the universe. The answer, of course, is that none of us are alone. We're all connected through the vast cosmic web of matter and energy that makes up our galaxy. The same atoms that form 3I Atlas also exist in our bodies. The same physical laws that govern the comet's formation also governed our own. We're part of the same universal story, separated by distance, but united by the fundamental nature of reality itself. This brings us back to what makes 3I Atlas truly special compared to Oumuamua. Yes, the earlier observations were more limited. Yes, we learned less from that first interstellar visitor than we're learning from this third one. But the real difference lies in what these objects represent about our growing capability to study the universe. When Oumuamua raced through our solar system in 2017, we were caught unprepared. Our detection systems weren't optimized for finding such objects. Our observational protocols weren't designed for rapid response to interstellar visitors. We did the best we could with the tools we had, but we knew we could do better. The experience with Oumuamua taught us valuable lessons. Survey telescopes were upgraded, and their search algorithms refined. Communication protocols were established for quickly alerting the global astronomical community when something interesting appeared. Observation strategies were developed for maximizing the science return from fleeting opportunities. The astronomical community essentially went to school on Oumuamua, learning from both our successes and our missed opportunities. 2I Borisov benefited from these improvements. The response was faster, the coordination better, and the scientific yield greater. But even then, we knew we could do more. The fleet of spacecraft now observing 3I Atlas didn't all exist in 2019. The James Webb Space Telescope hadn't launched yet. Several Mars missions were still in development. Our capabilities have continued to grow. With 3I Atlas, we're seeing the full maturation of humanity's interstellar visitor observation program. This isn't just one mission or one telescope doing the work. It's a coordinated global effort involving dozens of facilities on Earth, in Earth orbit, and spread throughout the inner solar system. The observations span the electromagnetic spectrum from radio waves to gamma rays, providing a comprehensive view that no single instrument could achieve alone. This multi-wavelength approach is crucial because different types of light reveal different information. Visible light shows us the dust and reflected sunlight. Infrared light reveals temperature and can penetrate dust clouds to see the nucleus more clearly. Ultraviolet observations can detect certain molecules that don't show up strongly in visible light. Radio observations might detect specific molecular transitions that reveal chemical composition. The data management challenge alone is formidable. Each observatory is generating enormous amounts of data, terabytes of images, spectra, and measurements. All of this data needs to be processed, calibrated, and archived. Different instruments have different data formats and characteristics. Bringing it all together into a coherent picture requires sophisticated software and skilled analysts who understand both the science and the technical details of each instrument. Yet this is exactly what's happening. Research teams around the world are sharing data, comparing results, and building a comprehensive understanding of 3I Atlas that far exceeds what any single team could achieve alone. This collaborative approach represents modern astronomy at its best. Scientists working together across national and institutional boundaries, united by curiosity and the desire to understand our universe. The public communication around 3I Atlas has also been notably different from Oumuamua. With our first interstellar visitor, the communication was sometimes confused and contradictory. Speculation ran rampant, particularly after a controversial paper suggested Oumuamua might be an alien spacecraft. While that paper was widely criticized by the astronomical community, It generated sensational headlines that sometimes overshadowed the actual science. With 3i Atlas, the messaging has been clearer and more consistent from the start. This is a comet. It's from outside our solar system. It's scientifically fascinating, but not threatening. It's behaving in ways that mostly match our expectations based on solar system comets, with any differences being subtle and requiring careful analysis to detect. The absence of wild speculation doesn't make the story less interesting. If anything, the real science is more compelling than any science fiction scenario. The naming convention itself helps with clear communication. 3i Atlas immediately tells you this is the third confirmed interstellar object discovered by the Atlas survey. Compare this to Oumuamua, which, while meaningful in Hawaiian, didn't immediately convey the object's nature to non-specialists. Clear, systematic naming helps scientists communicate efficiently and helps the public understand what they're hearing about. As 3i Atlas continues its journey through our solar system over the coming months, the observation campaign will evolve. Different instruments will take the lead at different times, depending on the comet's position and activity level. Ground-based telescopes will conduct most observations while the comet is far enough from the sun to be easily visible in dark skies. As it approaches closer to the sun, space-based instruments like Hubble, Webb, and SOHO will become increasingly important. The period around closest approach in late October 2025 will be particularly intense. This is when the comet will be most active, releasing gas and dust at maximum rates. It's also when solar heating will be strongest, potentially triggering outbursts or revealing structures on the nucleus surface. Every telescope that can safely observe the comet during this period will be watching. Then comes the passage behind the sun from our perspective, when 3i Atlas will be temporarily unobservable as it's lost in the sun's glare. This gap in observations will last several weeks, from late September through early December 2025. During this time, astronomers will be processing and analyzing all the data collected during the inbound phase, preparing for the renewed observations when the comet reappears. The outbound observations beginning in December 2025 will be critical for understanding how the comet's solar passage affected it. Did the nucleus fracture or fragment, a fate that befalls some comets during close solar approaches? Did an insulating dust layer form on the surface, changing how rapidly the comet deactivates as it moves away from the sun? Are there asymmetries in the outbound activity compared to the inbound activity? These outbound observations will also provide a final opportunity to refine our measurements of the nucleus size, rotation, and composition. As the comet recedes from the sun, its activity will gradually decline, eventually reaching a point where the nucleus becomes visible without being completely shrouded by the coma. This will allow for direct observations of the solid body at the heart of all that dust and gas, providing size and possibly shape measurements with better accuracy than was possible when the nucleus was hidden within its dusty cocoon. The observation campaign is expected to continue until 3i Atlas becomes too faint for even our most sensitive telescopes to detect. This will happen sometime in mid to late 2026, when the comet has receded beyond several astronomical units from the sun and returned to its frozen, inactive state. At that point, 3i Atlas will fade into the darkness, becoming once again just another invisible wanderer in the vast space between stars. But the science won't end when the observations do. In fact, in many ways, that's when the real work begins. Astronomers will spend years analyzing all the data collected during the observation campaign, publishing papers, testing theories, and comparing 3i Atlas with other comets, both interstellar and solar system natives. Every detail matters, every measurement contributes to our understanding. Computer models of cometary structure and evolution will be updated based on what we learn from 3i Atlas. These models attempt to simulate how comets form, how they evolve over billions of years, and how they behave when heated by a star. Observations of real comets provide the reality checks these models need. When observations match predictions, it confirms our understanding. When they don't, it tells us we need to refine our theories. The story of 3i Atlas will also become part of the growing database of interstellar objects. With 3 confirmed examples now, Oumuamua, 2I Borisov, and 3I Atlas, we're beginning to accumulate statistics. What fraction of interstellar objects are asteroids versus comets? What's the typical size distribution? How do their compositions compare to solar system objects? These questions require multiple examples to answer, and each new interstellar visitor adds crucial data points. Statistical analysis might seem dry compared to the excitement of new discoveries, but it's actually where some of the most important science happens. Individual objects can be unusual, quirky, or affected by unique circumstances. But when you look at populations of objects, patterns emerge that reveal underlying physical principles. The more interstellar visitors we detect and characterize, the better we'll understand the typical properties of matter wandering between the stars. Looking toward the future, we can expect to discover more interstellar objects with increasing frequency. The survey telescopes that found 3I Atlas are part of a growing network of automated sky monitoring systems. These telescopes repeatedly scan large areas of the sky, comparing new images with previous ones to identify anything that has moved or changed. It's like a cosmic security camera system, always watching for visitors. The upcoming Vera Rubin Observatory, when it begins operations, will dramatically increase our discovery rate. This facility, currently under construction in Chile, will have a massive camera, the largest digital camera ever built for astronomy, capable of photographing the entire visible sky every few nights. Its sensitivity and coverage will make it a superb interstellar object detector, potentially finding dozens or even hundreds of these cosmic wanderers over the coming decades. Imagine what we'll learn when we have not 3 but 30 examples of interstellar objects to study, or 300. Each one will be a sample from a different planetary system, a different corner of our galaxy. Some might have unusual compositions that hint at exotic formation conditions. Others might carry organic compounds that inform our understanding of chemistry throughout the cosmos. The possibilities are extraordinary. There's even discussion of attempting a mission to rendezvous with an interstellar object, though the technical challenges are formidable. These objects are moving fast, tens of kilometers per second relative to our sun. Catching up with one would require enormous amounts of propellant, or perhaps exotic propulsion technologies like solar sails or nuclear electric engines. The mission would need to be launched quickly after an object's discovery, before it races beyond reach. Despite these challenges, conceptual studies are underway. Engineers and scientists are exploring what such a mission might look like, what instruments it would carry, and what science it could accomplish. Imagine a spacecraft actually touching down on an interstellar comet, drilling into its surface and analyzing material that formed around another star. The scientific return would be phenomenal, potentially answering questions we can't fully address with remote observations alone. Such a mission probably lies years or decades in the future. Current technology could probably accomplish it, but the cost and complexity would be substantial. Perhaps 3I Atlas or a future interstellar visitor will prove so interesting that it motivates the funding and effort required. Or perhaps advances in propulsion technology will eventually make such missions more practical. Either way, it's exciting to think about the possibility. In the meantime, we continue to learn from our current visitor. Every observation of 3I Atlas adds to our knowledge. Every analysis provides new insights. The comet is teaching us about the space between stars, about how matter travels through the galaxy, about the chemical processes that occur in planetary systems scattered throughout the Milky Way. It's a cosmic messenger, carrying information from regions of space we may never reach with spacecraft, at least not in our lifetimes. Think about what 3I Atlas represents in human terms. This comet is older than human civilization. It was already wandering through interstellar space when our ancestors were still learning to make stone tools. It drifted through the darkness while pyramids were being built, while empires rose and fell, while the scientific revolution transformed our understanding of nature. And now, in this brief moment of cosmic time, our paths have crossed. We've built telescopes powerful enough to see it. We've developed the mathematics to understand its motion. We've created instruments sensitive enough to analyze its composition from millions of miles away. We've learned to work together across nations and continents to study it comprehensively. In a very real sense, 3i Atlas is meeting humanity at our scientific peak, at least so far. We're showing this ancient wanderer the best of what our species can do when we turn our curiosity and ingenuity toward understanding the cosmos. The encounter is temporary. 3i Atlas will soon continue its journey, leaving our solar system behind and returning to the stellar wilderness. But the knowledge we gain from it will persist. Future generations will read about this comet in scientific papers and textbooks. They'll see the images captured by Hubble and Webb, the data collected by our fleet of observatories. They'll build upon the foundation of understanding we're establishing now. And perhaps, someday far in the future, another civilization around another star will detect 3i Atlas passing through their celestial neighborhood. They'll turn their own telescopes toward it, conduct their own observations, and wonder about its origins just as we have. They might never know that this comet once passed through a solar system where a species called humans studied it with wonder and curiosity. But in a sense, 3i Atlas will be carrying a message from us to them. A message written in its surface chemistry, in the subtle alterations caused by its passage near our sun, in the atoms that our world contributed to its ever-evolving composition. This is the grand story that 3i Atlas connects us to. We're not isolated inhabitants of a single planet orbiting a single star. We're participants in a galaxy-wide exchange of matter and information that's been happening for billions of years and will continue for billions more. Every atom in your body has traveled through space, perhaps carried by ancient comets or expelled from dying stars. We are quite literally made of stardust, and objects like 3i Atlas remind us of this profound connection. The comet also reminds us how much we've learned and how much remains unknown. We can calculate its trajectory with incredible precision, predict where it will be years in advance, and analyze its composition from millions of miles away. These are remarkable achievements, the result of centuries of scientific progress built upon the work of countless researchers across generations. Yet for all our knowledge, mysteries remain. We still don't know the exact star system where 3i Atlas formed. We don't know what events led to its ejection into interstellar space. We don't fully understand why some comets fragment during solar passages while others remain intact. We can't yet explain all the subtle details of how cometary nuclei evolved over millions of years in the cold of interstellar space. These mysteries aren't failures of science. They're invitations to future discovery. Every question we can't yet answer represents an opportunity for someone watching this video right now. Maybe you'll be the scientist who develops a new technique for tracing interstellar objects back to their origin systems. Maybe you'll be the engineer who designs the propulsion system that finally allows us to rendezvous with an interstellar visitor. Maybe you'll make a discovery we can't even imagine yet because the necessary technology or concepts haven't been developed. The journey of scientific discovery is ongoing, and every generation adds to it. The astronomers observing 3i Atlas are standing on the shoulders of those who came before them. Galileo, who first turned a telescope to the heavens, Newton, who deciphered the mathematics of orbital motion, Oort, who predicted the vast cloud of comets surrounding our solar system, and countless others whose work laid the foundation for today's observations. In turn, today's scientists are creating the foundation for tomorrow's discoveries. The data being collected on 3i Atlas will be archived and preserved, available for future researchers who might have new questions or new analysis techniques we haven't invented yet. Some of the most important scientific insights come from reanalyzing old data with fresh perspectives or new methodologies. The story of 3i Atlas also illustrates how modern science has become a truly global endeavor. The comet was discovered by a telescope in Chile, confirmed using observations from facilities around the world, and is being studied by an international fleet of spacecraft. Scientists from dozens of countries are contributing to the research, sharing data and insights across borders. Astronomy has always had an international character, but modern communication technology has accelerated collaboration to unprecedented levels. This global cooperation represents something hopeful about our species. Despite our differences, despite conflicts and disagreements, we can still come together in the pursuit of knowledge. The same curiosity that drove ancient humans to study the night sky continues to unite us today. When we look up at the stars, national boundaries become irrelevant. We're all citizens of Earth, inhabitants of a small blue planet, united in our wonder at the cosmos. 3i Atlas offers us perspective on our place in the universe. Our solar system, which seems vast from our human perspective, is just one of hundreds of billions of planetary systems in our galaxy. And our galaxy is just one of hundreds of billions of galaxies in the observable universe. The comet's journey through interstellar space reminds us of the immense scales involved, the vast distances between stars, and the patience required for cosmic voyages. Yet despite these enormous scales, we're connected. Matter flows between stellar systems. Comets carry samples from one neighborhood of the galaxy to another. The same physical laws apply everywhere, creating a fundamental unity beneath the surface diversity. Whether a comet formed around our sun or around a star hundreds of light years away, it's made of the same elements, governed by the same forces, shaped by the same processes. This uniformity gives us confidence that what we learn from studying 3i Atlas applies broadly. The insights we gain about cometary composition and behavior aren't just relevant to this one object or even to interstellar comets generally. They inform our understanding of how planetary systems form and evolve everywhere in the universe. They help us interpret observations of dusty disks around distant young stars. They guide our models of how rocky planets acquire their water and organic materials. As we approach the conclusion of this cosmic journey, it's worth reflecting on what makes 3i Atlas genuinely special compared to Oumuamua. Yes, we're gathering more data. Yes, our observations are more comprehensive and coordinated. Yes, we're benefiting from improved technology and lessons learned from previous interstellar visitors. But the deepest difference is this. 3i Atlas represents a coming of age for humanity's ability to study interstellar objects. Oumuamua was our awkward first encounter, filled with surprises and missed opportunities. 2i Borisov was our second chance, when we did better but still had room for improvement. 3i Atlas is our mature response, showcasing our full capabilities and demonstrating that we're ready for whatever the galaxy sends our way next. We've developed the infrastructure, the expertise, and the coordination to do this right. This progression from Oumuamua to 3i Atlas mirrors the broader story of scientific progress. We learn from experience. We improve our tools and techniques. We build institutional knowledge and develop best practices. Each generation of scientists stands on the achievements of the previous generation, reaching a little higher, seeing a little farther. The observation campaign for 3i Atlas will continue for many more months, and the analysis will extend for years beyond that. New papers will be published, new insights will emerge, and our understanding will continue to deepen. The story isn't over. In many ways, it's just beginning. But what we've learned already confirms something wonderful. The universe is knowable. Through careful observation, rigorous analysis, and collaborative effort, we can understand cosmic phenomena, even when they originate from beyond our solar system. So when you look up at the night sky tonight, remember that somewhere out there, invisible to your eyes but real nonetheless, 3i Atlas is continuing its journey. This ancient wanderer has traveled for millions of years through the cold darkness between stars, and for a brief moment, its path intersected with ours. We had the good fortune to notice it, the technology to study it, and the curiosity to want to understand it. 3i Atlas will leave our solar system, but it won't leave our knowledge. The data we've gathered, the insights we've gained, and the questions we've raised will continue to drive scientific inquiry for years to come. And when the next interstellar visitor arrives, whether it's 4i or 5i or some future designation, we'll be ready. We'll turn our telescopes toward it with confidence born of experience, eager to learn what new secrets it might reveal about our magnificent, mysterious universe. The cosmos is vast beyond imagination, filled with wonders we're only beginning to discover. Objects like 3i Atlas are cosmic gifts, opportunities to expand our understanding and glimpse the workings of nature on the grandest scales. Every one we detect and study brings us closer to answering the fundamental questions that have driven human curiosity since our species first gazed upward and wondered about the lights in the sky. We are made of stardust, participants in a cosmic story billions of years old and still unfolding. 3i Atlas is a fellow traveler in that story, a wanderer whose path briefly aligned with ours. We've studied it, learned from it, and been reminded of our connection to the wider universe. And that connection, that sense of participating in something vast and ancient and magnificent, is perhaps the greatest gift these interstellar visitors bring us. Thank you for joining me on this journey through the cosmos. Keep looking up, keep asking questions, and keep that sense of wonder alive. The universe has many more surprises waiting for us, and the adventure of discovery continues. If you enjoyed exploring the mysteries of 3i Atlas, make sure you're subscribed so you don't miss future updates as this story unfolds. The cosmos is calling, and there's always something new to discover.